Okay, for the last lesson in trigonometry, we're going to look at the applications involving the sine law and the cosine law. So problems in trigonometry can be solved using either SOHCAHTOA, if I can create right angle triangles, the sine law, or the cosine law, or a combination of multiple of these. We can also use the Pythagorean Theorem, as we already know. In all cases, three pieces of information are required, one of which must be a side length. If I only know angles, then I can't derive the side lengths from that. But if I know at least one side length, then any other combination I should be able to solve. Use the following to determine which method is appropriate. Anytime I have a right angle triangle, I'm just going to use SOHCAHTOA. So the sine ratio, cos ratio, or tan ratio. I'm going to use this cosine law if I'm given either three side lengths or two side lengths and the angle in between them. I'm going to use the sine law in the other cases being if I have two side lengths and an angle that is not contained, or if I have two angles and a side length, because I can always solve my third angle and use my sine law. There are many practical examples in which students have to choose the appropriate method for the solution. We introduce the applications of trigonometry and circles and the concept of bearing since they provide further application of the sine law and cosine law. So first, we're going to look at trigonometry and circles. Complete the following circle properties from earlier math courses. The diagrams are provided as an aid. Well, first, we say if the perpendicular from the center of a circle to a chord is going to bisect. Example A is an example of this, where at this point, where if I'm creating a perpendicular to this chord where it's connecting between points A and D, we call that bisecting. For B, the measure of the center angle, the angle at O here, is equal to blank, the measure of the inscribed angle subtended by the same arc. Well, I'm going to say that that is going to be double. That's a fancy way of saying if I look at, for example B, angle X is going to be either 2 times angle Y or 2 times angle Z. The inscribed angle subtended by the same arc are equal, which means that if angle Y and angle Z are created by taking any point along the circle and then connecting to the two exact same points, so here I have one triangle that's created, here I have the other triangle that's created, but they share 2 points, C and A, then that means that angle Y has to be equal to angle Z. So these two are going to be the same because they share 2 of the same points and go around. The third point is another point that is on the circumference of the circle. A tangent to a circle is, as we can see here, perpendicular to the radius of the point of tangency. So if I say it's tangent, then it touches it once, never touches again, and this tangent line is going to be perpendicular to whatever my radius was. Okay, so in the diagram, O is the center of the circle. It has a radius of 3.25, and from length QR, so this length here, is going to be 2.5 centimeters, and the length r to s is going to be 4.7 centimeters. This also means that the length here is going to be 3.25 because it's going to stretch from the center out to the side, and at the same rate the length here also has to be 3.25. The first thing that it wants to know is what is the length of P to Q. Well, if this length is 3.25 and this length is 3.25, then I can say that the length of P to R is going to be 6.5 centimeters for that total length. So now I have this right angle triangle where I can use the Pythag to solve that. I can say that in this case PR is going to be the hypotenuse, and the two legs are going to be from QR and PQ. This means that PQ squared is going to equal PR, or 6.5 squared, minus, when you move the QR to the other side, 2.5 squared, which would give me 42.25. Oh, sorry. No, when I subtract them, it's going to give me 36. Which means that PQ is going to equal the square root of 36, which is just going to equal 6. So I can say that this side is now 6 centimeters. What is the measure of angle Q to P to R? So what is the measure of the angle that exists in there? So if I go from Q to P to R, I'm looking for angle P. Well, in this case, I can say that if I have sine of angle P, it's going to equal P's opposite, because I know this is still a right angle triangle, 2.5 divided by the hypotenuse, which is going to be 6.5. Which means that angle P is going to equal sine to the negative 1 of 2.5 over 6.5. And that angle is going to be 23 degrees. Now what it wants to know is what is the angle of S to Q to R? Well, if I'm just looking at this and I go from S to Q to R, it's just going to be part of this triangle, where if I'm trying to solve SQ to R, I just want to know what that angle is. Well, if I know that Q to R to S, Q to S to R is going to be the same as this angle P, because they have the same chords. That's going to be 23 degrees. So I can say that angle S is equal to 23 degrees. Now, I need to figure out another side because I don't know what this angle is and I don't know what this angle is. So first, I'm going to use the sine law to figure out what this angle is. And I can say that, well, if I know that this is 4.7, I know what this angle is, and I know what the opposite side length is. Let's just pull out this triangle for a second just so I can make it a little easier to see. I have this triangle which is Q, R, and S. We know that this is 23 degrees. We know that this is 2.5 centimeters, and we know that this is 4.7 centimeters. Well, if I'm trying to solve for this side length here, I can use a sine law because I know S, I know its opposite, and I know the opposite of Q. Which means that when I'm solving for this one, I'm going to say that if I'm trying to solve for angle Q, sine of Q divided by its opposite, 4.7, is going to equal sine of 23 divided by its opposite of 2.5. Which means that sine of Q is going to equal 4.7 multiplied by sine of 23, all divided by 2.5. Which means that angle Q is going to equal sine to the negative 1 of what all that is. If I put that in my calculator, I'm going to get approximately 0.7346. And sine to the negative 1 of that is going to be 47 degrees. So in this case, I needed to use right angle and SOHCAHTOA to solve for what this angle was. I used that angle, knowing that that was the same as this one, and then I used the side lengths given and the sine law in order to solve my other missing piece.